Howdy everyone, Nir Regev here. So today we're going to start with covering all the tutorials in the Circuit of Knowledge with video lecture for each and every one of them. This is an I'm going to be doing in the next 3 to 4 months, because there are almost 100 tutorials there and papers. And so this is the first one. So the Circuit of Knowledge, if you don't know, is a paid section in my website. It's a Circuit of Knowledge club. It's called drnirregev.com/Circuit of Knowledge Premium. This is the link, and inside you will get a section of a lot of tutorials covering many topics: AI and machine learning, for example, probability theory, radar theory, and so on and so forth. In each and every page here, there are sub-pages with the tutorials. Example, let's see, AI and machine learning, support vector machines. So you have support vector machines for iris species classification, and this is a tutorial on this subject. But today we're going to dive into the probability theory section, and we're going to discuss the elegant and very cool Buffon's needle problem. So what is it? In probability theory, Buffon's needle problem is a problem that was first posed in the 18th century by George Buffon. It is a classic problem in geometric probability that can be used to estimate the value of pi. And the idea is simple. We have a needle and we let it drop on the floor, and the floor is separated by lines. Okay? Every line, the distance between these lines is capital D, and the length of the needle is capital L. And the needle can fall and cross a line, or it can fall like here without crossing any lines, like here. Okay? Now, apparently, we can mathematically derive the ratio between the probability, we can mathematically derive the probability of a needle crossing the line, and this probability is related to the number pi. And if we actually estimate this probability, then we can leverage that to calculate an estimate for pi, for the number pi. Okay, how do we do that? Okay, so assumptions. The distance between the lines is D, like I said, the length is L, and the needle is dropped randomly in both position and orientation. Orientation, it means that the does in respect to the two XY plane, to the two D axis, is theta. The range of the variables. The range of the variables, theta is going between 0 and pi, and x is between 0 and d over 2, because the center of the needle can be at most d over 2 meters, let's say, away from the nearest line to ensure that the needle can cross that line. Needle crosses a line condition. The condition is L over 2 times sine of theta is greater than x. Or in other words, x, the distance between the center of the needle, let's say here, the center of the needle, let's say it's here, the distance between the center of the needle and the closest line, okay, is greater or equal than L over 2 sine theta, this distance. Alright, sorry, I said greater or equal, and it's actually less or equal. Okay, how do we calculate the probability? The total area and the x theta plane is double integral between 0 and d over 2, between 0 to pi on d theta dx, and the result of that is d pi over 2, and this is where pi gets into the game. Okay? For the needle to cross the line, we have this condition. So if we want to calculate the area of crossing region, okay, then we have to calculate this area, and here we're counting over x only between 0 and L over 2 sine theta, and this will be the area in which on the plane in which the needle is crossing a line. A needle is crossing a line. The ratio between these two, the area of crossing divided by the total area, is the probability of the needle crossing a line. Okay, the first integral we derive it to be d pi over 2. The second integral, after we derive it, it's L, and so this is the ratio. This is the probability. Okay, so if we can estimate this probability, let's say we throw a lot of needles on the floor and count, or we do it in a computer program in Python, let's say Monte Carlo simulation, then we can extract pi out of this equation and use the probability that we estimated and the known length to estimate pi, right? So we can see here that pi is approximately 2ln over dc. Okay? And c over n is the relative frequency. C is the number of observed crossings, and n is the number of total dropping of a needle. Okay? How do we do it in code? We do it let's say 10,000 times. It's a Monte Carlo simulation. The needle length is 1, let's say meters. The line distance is 2. And we are running in a for loop on the number of needles, which is 10,000 in this case. And we're counting all the crosses. Then we're estimating pi using the formula above. So it's 2 times the needle length times the number of needles divided by crosses times line distance. And we print everything, and we can see that we get a number that is very close to pi. We get a number of crosses which is out of 10,000, 3,175. And you can see that as we go along and throw more and more, the estimation for pi converges to the actual value, which is the red line. Okay, so that's it for this lecture on Buffon's needle problem. Thank you for listening so far. Please feel free to subscribe and like if you like this channel and if you like my content. If you want me to talk about other stuff, please let me know in the comments. If you have any questions, also let me know in the comments. And don't forget to subscribe to our Circuit of Knowledge Club. Again, it's drnirregov.com/Circuit of Knowledge Premium.